Welcome to anyone watching this video. What it shows is a prototype caution light panel that I've built for the A10C Warthog for Digital Combat Simulator. This is a key panel that I wanted as part of my SimPit, which I'm going to build later in the year. And the software, the program that is used here is DCS BIOS, and it's that software that allows the simulation to talk to the physical panel that I've built. So with that said, a big shout out and a thank you to FSF Ian for all the great work he's done in developing DCS BIOS. And here you can see a demonstration of the panel in use, and clearly what is happening within the simulation is outputs on the physical caution light panel. And whilst this test is looking at the panel in what would be typical lighting conditions of the SimPit, this next test now is a test where it's looking at it in the brightest environment you could get, just to check that even in such an environment you can actually see what's happening, which has been illuminated. And also this test goes along with looking at some of the other physical panels that I've built and testing how they all work together. What I can say in using this is, compared to clicking with the mouse, the toggles within the simulation, to physically interact with the real toggle switches and the real physical panels, it just adds so much to the immersion and so much to flying the aircraft. For anyone that's potentially looking to build a caution light panel for their SimPit, I have added on some extra footage now just to go into a little bit more detail on how I built this. So the microcontroller that will be used will be an Arduino base one. That's obviously what works with DCS BIOS. So in this case, what I've shown here is how my Arduino Uno is connected from a wiring point of view to the MAX7219 LED board. So as can be seen from the Arduino, you've got the power output, which is 5 volt, which it goes to the VCC. You've got the ground pin, which obviously goes to the ground of the driver board, and then you've got the 3 pins on the Uno, which go to the DIN, the CS and the CLK inputs to the board. Now this breadboard view on the right hand side of it, what it shows is just representative of the MAX7219 breakout board. There is more to the actual boards, there's resistors and capacitors and other bits on, but what this is showing here is just drawing your attention to the legs of the actual chip, which serve the functions of segments and digits. They branch out on the PCB to the green output pins that I'm highlighting there. And now this is the MAX7219 driver board up close. And the real trick with this is to understand of the pin outputs that you'll see 8 at the top and 8 at the bottom, which of those are for the digits and which are for the segments. Because when you look at the legs, which branch off the actual microchip, it's not clear, even by looking at the trace lines on the PCB, which goes to where, and they don't follow any particular logical order. You could almost expect the top row of 8 is for the digits and the bottom row is for segments, but that's not actually the case. The starting point to map the output pins on the driver board is to look at the pin configuration on the data sheet for the MAX7219 itself. What we're interested in looking at this schematic is which of the legs that branch out from the chip are for the digits, which are digit 0 to digit 7, and then which are the ones that are for segment DP and through each of the segments to segment G. When you pick up the driver boards online, and you can get them for literally a couple of £, it's probably worth getting one that's the pre-soldered one, but also the one that comes as a kit that you put together, because it's using that kit and it's using the blank PCB, which we'll have a look at now, that you can work out using that which of the legs of the chip in terms of digits and segments branches out to which of the output pins. So to confirm, what we're looking at is the legs on the left hand side and the right hand side, and where they then branch out to at the top there and at the bottom on the output pins. Using a basic 9-volt circuit, where the one end of that circuit will connect it to, in this case, the second leg down, which is the second pin, which is digit 0. And then the other end of the circuit we can run across the output pins until we find the output pin which completes the circuit, and then we know that that output pin is digit 0. So the next one would be to move to the third leg down, which would be digit 4, and then to again look for the output pin which connects and completes the circuit, which we can see here, and then just repeat that over and over until the whole driver board's mapped out. And what you can see now is a PCB view that I've put together showing the fully mapped out driver board, and from that board you can see for each of the digits and each of the segments which corresponding output pin it has. Through various tests with this driver board, I've been able to establish that segment F and segment A they're not used. Ultimately, the driver board will allow a matrix of 8x8, but to produce a caution light panel and using the DCS BIOS code, our matrix is going to be 8x6. It would appear, unfortunately, that not all driver boards have a standard PCB layout, so even though this one I've mapped out, when I've then had other ones I've bought offline, they have a completely different setup. So via the method shown, it's a good way to work out for that particular board you've got which pin is for which output. And when picking these up online quite cheap, they don't tend to come with a data sheet from the manufacturer. And I can now start testing the output to an LED matrix, starting with an 8x8 that comes with the LED driver, which you can see here. You can see two lines that are permanently lit, and that represents the segments A and F, which aren't effectively used for this. I now run a test to part build a matrix, looking at two lines of the caution light panel here, and at the same time just testing different LEDs for brightness. And it's now time to build my first matrix. So this is a 6x8. The layout is not how it would be in the final panel, but it just allows me to run all the other tests to fully understand exactly how the matrix would work. Something to be thinking about at this stage is what would be the LED that will give you the greatest brightness, but at the same time the power that it needs is such that it doesn't need a separate supply, and it can be powered from the LED driver board just from the power that's fed from the Arduino itself. And this becomes a test bed by which we can fully learn everything about the matrix and how it works. With everything learnt to this point, it's now time to produce a schematic for the matrix that I'm going to build. And you can see the digits I'm highlighting there and the segments, and how they will cross the anodes and cathodes of the LEDs. An important consideration will obviously be the use of resistors with your LEDs. I've tested all kinds of LEDs. Many of them actually had resistors. Some of these ones I've picked up here online are 12 volt LEDs, and the matrix as I've built here, as you can see, doesn't have any additional resistors in, but that's something that you will want to look at carefully when designing your own matrix. With the LED matrix built, you can take a multimeter and you can take that to the legs of any one of the LEDs, and then you can see the voltage that's running through it, and you can also see the current it's drawing in milliamps. And then when you look at that compared to the data sheet, you can then be happy that it's running all in line with the tolerance of that LED. The sketch that I have here has several parts to it which I've modified and I've adapted. The one is the area just highlighted now, which is a pin designation, because obviously that has to be correct to match the output pins you've used on the Arduino to the driver board. The Arduino code on the right hand side is laid out exactly as you would look at the caution light panel. So the segment stated in the top left of that part of the code and the digit stated in the top left of that part of the code represent the intersection of the matrix that would illuminate when the top left part of the actual caution light panel within the simulator would be activated. So in this case that would be the engine start cycle. So if that's triggered within the simulation, then via this code it says wherever digit 0 and segment DP intersect, that's the LED that will illuminate. As you then look at the schematic, you'll notice that digit 0 and segment DP intersect in the top right as opposed to the top left, and the reason for that is the schematic is as you wire the matrix at the back of the caution light panel, so for that reason it is a mirror image of the other. And you therefore could say that the schematic represents the code flipped vertically on its axis, if that's an easier way to picture that. Based on the tests that I did, I felt that the schematic I've got here is what works for me, particularly in terms of how I've took the wiring from the segments that run across and intersect with the digits, sort of spanning outermost to outermost with the segment DP to the innermost with segment G, and then that was where I just had to adapt the code to just reflect how the segments swept across the digits. The small part of the code that's highlighted now is just the digit for the intensity of the LEDs, that being the brightness, which can be a figure up to 15, and I found that having it set at the maximum worked best for the type of LEDs I used. So a shout out to FSF Ian for the sketch that he had produced and published on the ED forums, which is the one that I've used here and just made those 3 changes to, so it works with my particular panel. When you're at a point that you're happy that you've got your matrix all planned and you know exactly how you're going to build it, you can then have a look to build your actual the fascia to the panel, which for me will be made up of 4 layers. The first 2 of which you can see here. The layer 1, which is on the left, will be a 3mm black acrylic, which will have 48 cutout windows, and that will sit on top of layer 2 to your right, which is some spray painted Opal Acrylic with the various text engraved, which we'll have a look at now, the both of them, for the preview function of how they will look when they're cut on the CNC machine. I think for the panel to look right visually, you definitely need some form of division in between the of the text for the columns and rows, and the way that looks inside the actual A10C in the simulation is almost like there's indentations that run between them. Now the way I plan to achieve the division on mine is, as I say, to have this layer 1 on the left, which will sit on top of layer 2. So we'll have a very brief look now at the CNC running its program based on the CAD CAM file that we produced for layer 1, and now moving on to layer 2. It will finish layer 2 by a cut of that acrylic piece, just so it's all to the same dimensions. The overall panel front will have a layer 3 and 4, which in this case I've chosen 9mm MDF. On the left you can see that has a series of cutouts as windows, which will house the LEDs, and layer 4 on your right again is an MDF, thickness being just about right where the legs of the LEDs will pass through it and protrude sufficiently on the other side to wire the matrix, but can be done in such a way that it holds it quite firmly. And the preview function now gives us an idea of what that will look like when it's cut on our mill. And if we have a close look at layer 3 and we remove just a couple of the waste segments of material and then have a closer look, you can see compared to layer 1 you can really see the extra thickness. This isn't 3mm, it's 9, and look, as a pocket of what we've got now, that will be sufficient to allow for the height of the head of the LED. And when layer 2 is attached quite firmly and tightly to this, it should mean there's minimal bleed of light between the windows. And if we now have a close look at layer 4 on the right hand side, we can see the drill holes for the legs of the LEDs to pass through. And if we rotate this round, where we look now at where the legs of the LEDs will protrude, this is where the matrix will be wired to the back of this that you're looking at now, and the schematic we looked at earlier is what will be mapped onto that. So as before, we'll just take a brief moment just to have a look at the production process on the CNC for those 2 layers. So one single sheet of MDF does the trick here, simplifies the setup, and we just can execute the program to cut into these. Here are the 4 layers, which will be put together to make up the single front unit, which the matrix will sit at the back of, and then there'll be other components of the microcontroller and the LED driver board, which will all be wired up and connected to it, but held on suspended pieces of see-through acrylic, which spacers will hold in place and form the overall structure to the unit. And it does look like layer 2 did pick up a few marks at different points throughout its production, which, if it was the main single, if that represented a layer 1 to another panel, not quite sure if I'd actually want to use that as a finished item, but by the time layer 1 sits on top of it, it seems that fortunately some of the cross lines of that layer 1 will actually hide a couple of the marks. So this is the first time I've used a MDF material in one of my panels, and it did work very nicely. The holes for the legs of the LEDs are purposely at a diagonal, and the reason is when one line of wires runs across the anodes and the other the cathodes, having the legs at a diagonal ensures that it's easier to avoid the overlap of connecting wires. And it's nice to start putting this together now. You can see layers 1 and 2 put together on the left, and layers 3 and 4 put together on the right. And as we have a close look at that, it's turned out quite nicely. A good finish. The pockets here house the heads of the LEDs nicely, so when the LED sits near what will be layer 2 above it, it's not too close, but equally it's not too far away, it's just sufficient to cast the light. With it being a prototype, the wiring of the matrix isn't pretty, but it's functional, it does the job. I'll run a test to check that the new matrix is running as it should, and also a series of stress tests where I leave it on for long periods with all of it lit to just ensure that there's no failure within the matrix. There are several aspects of this panel that I will want to work on, and rather than dealing with one sealed unit that's difficult to get into, I've made it modular, where it can be, the front can be disconnected to the back, so they are more easily able to dip in and out of work to the matrix and work on the microcontrollers and the wiring of them. What we have now is the finished unit. There are several areas of a rework that I'm looking to do. On reflection, I think that layer 1 should be a matte black finish rather than a gloss, which gives reflection. The wiring of the matrix itself and the microcontrollers will need tidying up, and a fair number, probably at least 15, of the windows of text do need more than one LED, and ultimately I do want to look at the option of putting 2 LEDs in those windows, the ones where the text is a wider number of characters, so sometimes the lighter's cast doesn't quite extend from one side of the window to the other. But it's been great to build and great to use in flight, and I hope anyone that's watched this that's looking to build one has been able to take something of some value away from it. Thanks for watching.